Imagine getting in your car in the middle of the night. It's pitch black out, you get behind the wheel, and you're going to go to the grocery store with no headlights. You're only going to use your speedometer and a compass. Yeah, that doesn't make a lot of sense, does it? You wouldn't drive in the dark using only a speedometer and a compass. Now, these may be useful to tell you where you're going or if something happened, but it won't allow you to correct. In fact, in the world of navigation, this kind of approach is called dead reckoning, and there are lots of jokes about the word dead when it comes to dead reckoning. You can check those out yourself. But if we're to try to control something using only a number like a speed or a number like a direction, we're basically working like the world of surfaces, only using an RA value. A number might tell you something changed, but it doesn't tell you what to do about it. A number doesn't describe if our surface was turned and something went wrong in the turning process and it decayed at the end from a nice evenly spaced turning to a bunch of garbage, or if our plateaued surface suddenly turned into a peaky surface. The picture describes what's happening, just like looking out the windshield in your car. So let's talk a few minutes about the picture and understanding what is actually going on when we see a profile graph. Now, a plateaued surface is probably the most engineered surface of all, so let's start there, and here's a nice graph of a plateaued surface. The profile graph itself, just like in your science classes, has a scale associated with it. Our profile graph is going to be based on measuring some amount of millimeters along the surface, or perhaps inches in imperial. And that length that we measure is represented along what we call the x-axis. The y-axis, the up and down axis, is very different though. In the world of surfaces, the y-axis is scaled with much more magnification and usually it's in micrometers or perhaps micro inches. That's 1,000 times more magnification in that direction. In other words, if we took, let's say, that honing process, and we thought about the honing stone as being made up of abrasive particles, the honing stone itself is going to dig into our surface just along the bottoms of the particles. And these particles are going to have kind of U-shaped valleys as they scratch into the surface. But when we magnify this many times, the graph that we see is going to have wiggles, and then a very steep dip, and a very, very, very steep dip, and then another one, because we're magnifying those errors when we plot the surface. This magnification can fool us sometimes. We might fear that our diamond stylus won't be able to fit into the surface. But the diamond stylus, again, is operating in the real world, not the distorted world. So our measurements are great, but our profile graph is going to give us a picture of what's going on. So let's talk briefly about some of the pictures. For perhaps turning on a lathe, we might see a surface that has a repeating pattern. Now within the pattern, we might also see some fuzz or some randomness at the bottom. Perhaps that's a tool that's wearing out or a tool that's building up. And in other cases, we might have grinding, and if our grinder is starting to load up and burnish the surface, we might see the peaks are missing rather than a clean grinding process of peaks and valleys. So the profile graph is telling us the story of the process. Now here's another situation. A process like broaching or reaming, we might see surfaces occasionally. If we zoom in, we might see something like this, where one side of the valleys is steeper than the other side of the valleys. If you look at my plot here, you'll see that the left-hand side drops very steeply, and then the right side comes up more gradually. This can be an interesting indication of a problem in the material itself. Now I mentioned we're measuring with a diamond, and the diamond has an angle, and I also mentioned that this graph is going to distort our angles. Here's a situation in reaming, broaching, those kinds of processes where we actually smear material over a valley, and our surface looks like this, and the diamond, when it measures the surface, falls down, and then climbs back up properly. This will result in a profile graph with valleys that aren't symmetric. So as we zoom in and look at our surfaces, or perhaps use a tool like OmniSurf, which gives us the ability to plot things at a 1-to-1 scale, we can see these extra details in our profile graph. So to understand our surface, let's not use a dead reckoning approach. Let's actually go to the picture and relate it to the things that are going on, the things that matter in our processes and in our products. To find out more about your profile graphs, to discuss some of your data, we are standing by here at Digital Metrology and happy to help. Reach out to us at digitalmetrology.com.